In this video, we're going to take a look at a process of taking derivatives that's referred to as logarithmic differentiation. If you take a look at the starting definition, we can figure out very quickly what this process actually is. Logarithmic differentiation is a process of differentiating a function by first taking the logarithm of both sides of the function and then using implicit differentiation to find the derivative. Now, this might seem really weird, right? If you try to imagine some sort of a function, like I have y equals the sine of x, why in the world would I ever want to take a logarithm of both sides, that is, make the function more complicated, and then use implicit differentiation? How could this possibly be useful? Well, what we're going to see is that if I actually make use of some properties of logarithmic functions, then in certain select instances, this technique can be very, very advantageous. Now, we actually already talked about these properties of logarithms back in skills check number 2, but I'll re-highlight them here. The product rule for logarithms, remember, said that if I ever had a log with a base a of an x times a y, I could rewrite this, and I'll use a different color here. I could rewrite this as a log base a of x plus the log base a of y. That is, I could rewrite this log of a product as the sum of two different logs. The quotient rule also operated very, very similarly. Remember, it allowed us to take, that input should be x. It allowed us to take two logarithms, one with a log of x and another with a log of y, and just subtract them. I just have to remember that the numerator always comes first, since the order of subtraction matters. And then the very last one here, the power rule, said that we were able to go ahead and take this power of n and actually pull it down to the front of our logarithm, ultimately leaving us with n times a log base a of x. So these are our different rules that we have here, and we're going to see why exactly we can use these rules together with this process of logarithmic differentiation to potentially save some time when calculating certain complicated derivatives. So let's take a look here at example 3 for one possible example of when logarithmic differentiation is going to be really useful. So here I'm being instructed to use logarithmic differentiation to find the first derivative here. Now, the first thing that I should note is that logarithmic differentiation here is certainly not required. That is, I could find the derivative of this function without ever knowing anything about logarithmic differentiation. Right? I would start by probably using a quotient rule, and you could probably tell that it's going to be a little bit complicated because when I have to take the derivative of this denominator, I'm going to have to use a chain rule. And similarly, when I take the derivative of the numerator, I'm going to have to use a chain rule. Well, let's just take a look, though, at how using this process of logarithmic differentiation would actually help here. So to start, we'll take the logarithm of both sides. So I'll put here that we start by taking a logarithm of both sides of the equation. Now, you can really choose any log you want, like a log base 2, log base 50, it doesn't matter. For the sake of simplicity and writing as little symbols as possible, I always tend to go ahead and just use the natural log. If you don't like that, that's totally fine. You can use a different logarithm. There's no issue with it. Now, I'm going to go ahead here and immediately start to be thinking about what sorts of logarithm properties can I maybe make use of here before I start taking the derivative. Specifically, I'm looking at what properties of logarithms I can use to simplify this right-hand side. So I'll write here that using properties of logarithms, we can rewrite the right-hand side, this is a common abbreviation for right-hand side, as follows. Okay, so let's see. One thing that I might notice right away is that I have a logarithm of two things being divided. So I could rewrite this as a natural log of the numerator minus the natural log of the denominator. Okay? Oops, let me write it like this. Okay, so that's a good start. But I could also actually make use here of the power rule, Because I'll notice that this entire input on the logarithm is being raised to a power of 1/2. And so I could pull that down to the front and just leave everything else on the inside alone. In the same way, I could take this power of 5 and pull it down to the front and leave everything here on the inside alone. And now that I have things in this form, I'm going to go ahead and use implicit differentiation to do the derivative. Notice everything we've done so far has been purely algebra. So I'll state here, we now use implicit differentiation. And calculate. And let's see what we get. I'm going to go ahead and I'm going to take the derivative of the left-hand side. And I'm going to take the derivative of the right-hand side. Writing out all the detail here. It's 5 natural log 3x plus 2. Okay. So if I take this derivative, notice that on the left side, I'm going to have to make use of the chain rule. Because remember, I'm imagining this right now as the natural log of a bunch of stuff. So I'm going to end up with 1 over y times the derivative of y, which is dy dx. On the other side, notice I'm going to leave my 1/2, and I'll take the derivative here of natural log of stuff. So I automatically get 1 over that stuff, and then times the derivative of that stuff, which would just be 2x by the power rule. Then over here, I get the same thing. I have natural log of a bunch of stuff, so I'm going to have 1 over that stuff, and chain rule, I just multiply by 3. So notice I can very, very quickly get to a derivative, and in fact I can simplify this up a little bit more. If I wanted to, I could take dy dx and isolate it by multiplying y over to the other side. And I'm just going to put everything else over here in a big set of brackets. So notice that if I clean up some of the fractions that I have over here, I can see that like this 2 and this 1/2 are going to simplify down. And I'm just going to be left with a fraction of x over x squared plus 1. Over here, my 3 and my 5 multiply together to make 15, and I get 3x plus 2. So this right here is almost my final answer. Now technically I guess it could be a perfectly good final answer. It just contains both x's and y's. And so oftentimes what we'd like to do is to try to get this derivative completely in terms of x. And actually this is super easy to do because I only have to replace the value of y. And that value of y is really, really easy to replace because I was told at the beginning that y is equal to this big horrible fraction. So I'm going to go ahead here and actually just replace in that big scary fraction where y is. So I have the square root of x plus 1, 3x plus 2, that's all raised to the 5th power. And then I have my set of brackets. So I have this and then minus the 15 over 3x plus 2. And so here's a derivative of my original starting function. Now, as I state down here below, in this example up above, logarithmic differentiation was not needed. And in fact, you might be thinking to yourself, gosh, Kyle, what the heck? Like, this looks really ridiculous. Why would I go through all of this extra work dealing with logarithms, dealing with logarithm properties, doing implicit differentiation, worrying about substituting out my value of y at the end, when I could have just used the quotient rule? And I think if you're asking that question, you're spot on. That is a very legitimate question to ask, and I really don't have a good answer for you. I really can't think of much of a reason why, in this question, in example 3, why logarithmic differentiation is important to use. I would agree with you, and I would say it's not. But this then helps to contrast the idea of example number 4, when the process of logarithmic differentiation is imperative. It must be used. And we'll take a look at that example in the next video.